Welcome to the final presentation for our ice scraper project. As many people who live in Rexburg or other cold climates are probably aware, removing especially thick ice off of a car windshield can be really difficult on especially cold winter days. And some of the main problems with conventional ice scrapers that our group came up with have been difficulty removing especially thick ice, and especially for shorter individuals, the ability to reach the entire windshield can be challenging. Also, with regards to this project, being able to come up with an ice scraper design that would be able to mitigate both of those problems would be being able to make it affordable as well. So our project purpose was to design and fabricate an extendable ice scraper that can dispense de-icing fluid in order to optimize the efficiency of ice and snow removal on especially harsh winter days. So in this last presentation, we're going to go over a lot of basically the whole design process that we've gone through this semester. In previous design reviews, we've gone over benchmark products, patents, customer needs, performance measures, functional decomposition, concept generation and evaluation, the selected concept, prototypes, and a couple of engineering analyses that have been performed. And in this presentation, we'll go over all of those, as well as giving more details on the final product, the detailed design, cost analysis, and an additional analysis that was performed. So at the beginning of the semester, we did a bit of research to figure out some of the issues that people had found with previous ice scrapers. And so we looked at a lot of different benchmark products. Here are a couple of examples of products that we found. And we also did some research on patents for ice scrapers. And we were able to find one patent that resembled very closely the idea that we wanted to implement, but we weren't able to find anything with that design on the current market. From the ideas that we gathered from looking at patents and benchmark products, we were able to come up with a few customer needs that that customers seem to desire in an ice scraper. Also in reviewing online reviews, personal interviews, our personal experience, and with brainstorming as well. And from the customer needs statements, we came up with a few performance measures in order to measure each of those customer needs to verify whether or not we were achieving the desired requirements. Afterwards, we did a functional decomposition where we looked at all of the functions that the ice scraper would need to be able to perform. And that's listed in these diagrams right here. After doing the functional decomposition, we generated a few different concepts using those functions. Specifically, a couple of changes that we made were separating contacting ice and the snow, because those were going to be two separate functions in the final product, as well as clearing the ice and snow. Afterwards, we did a concept evaluation of each of the concepts that were generated, and we selected one concept overall that seemed to be the best. Doing a concept screening matrix, it seemed like we were able to come up with strong enough results that we didn't need to do a concept scoring matrix. It seemed pretty clear that many of the designs had similar features, and one of them was clearly better than the others. Afterwards, we began to build a few prototypes. In the top picture at the left and the picture at the right, those show our first prototype. And some of the features that were created in that prototype. This one was more of a rough prototype where we didn't think about all of the customer needs that were required, but mostly we were trying to obtain functionality out of this prototype. And we were able to get a spray bottle pump working in order to dispense some fluid, but there were problems with that system, and holding it together with duct tape wasn't as strong as we would need it to be. So we began designing a second prototype, and in a few slides I'll talk about what some of the major improvements were with that prototype. Afterwards, we did a couple of engineering analyses. We did a failure modes and effects analysis, where we looked at a couple of a few different ways that the ice scraper could fail, and a few actions that we could take in order to mitigate those modes of failure so that they would be as less likely as possible. And we also did an FEA analysis, looking at some of the stresses and deflections that would be involved during normal use. Using an applied force of 20 pounds, the results were maximum principal stress of just under 4,500 psi and maximum deflection of 0.2 inches. It turns out that the ultimate tensile strength of HDPE, which is what the material we were using to test, is somewhere between 1100 and 6200 psi. So the maximum principal stress may or may not be above the ultimate tensile strength, which would cause it to break depending on the specific HDPE that we decided to use. So our final product included these different components. We weren't able to take a picture after completing the assembly of the final product, but that was because we were going to continue working on the subsystem engineering phase of development, because there were some issues with the pumping system and getting everything to work out with regards to that. So we didn't end up getting a final picture of it, but these are the components that were used in it. So some improvements over the original prototype were that the extending handle was much shorter, so that it wouldn't be as bulky to store in its condensed form. The pumping system was also much more ergonomic and much stronger than just a spray bottle. The scraper and brush were more robust. It wasn't just duct taped together, so it was more stable. It would have been better for us to try and do the tests on scraping ice off of a windshield with this prototype as opposed to the last prototype. And we used epoxy to connect most of the connections, so that made everything a lot more stable as well. And without doing any performance measure testing due to safety and other limitations, we presumed that most of the customer needs were still met. We can go back and look at the customer needs statements, and we decided that 1, 2, 4 through 8, and 12 and 13, I believe, were all most likely met. Finally, in our detail design, we had this is a breakdown of all of the components of the system. So there's the handle with the pumping, or the plunger that goes into the pumping mechanism, the trigger that actuates that, the storage bottle that holds the de-icing fluid, the actual pumping system, and the tubing that carries the fluid from the pump to the nozzle at the end, and then the structure of the ice scraper handle and the ice scraper and brush itself. We also needed to make a custom part to be able to connect the pumping system to the ice scraper handle. And so that was designed in CAD and 3D printed. And there were a couple of other components, including an upgrade to this component that were also designed but were not able to be implemented. A cost analysis was also performed of the project. There were actually two different cost analyses performed. The first one analyzed the prices that we paid for all of the components that went into the final prototype. And that came out to just under $30. So the manufacturer selling price for that, for this assembly, would be a little under $60, which is very high. So we also did an analysis with taking mass production into account. And by estimating the prices that we would be able to find all of the components for, as well as assuming that we would be making the ice scraper and brush in-house, we were able to reduce the cost to a manufacturer's overhead of about $4, with manufacturer selling price of a little bit under $10, and customer actual selling price of just under $35. And when we had been doing personal interviews with customers to try to establish a price range for the final product, it seemed like customers were willing to pay somewhere around $25 to $30. So this estimate is fairly close to the desired market value. Additionally, in lieu of being able to perform all of the performance measure testing, we decided to go and do an additional fluids analysis to investigate the pump head that would be required for the pump to produce in order to achieve a nozzle velocity of 5 meters per second at the nozzle. So here's our diagram that goes over that. And initial calculations were performed to figure out the velocity inside of the tube relative to the nozzle velocity in order to perform the head loss calculations. And the Reynolds number, friction factor, and head loss were all calculated so that we could solve for the pump head, and that came out to be 16.7 meters. And fluid properties for ethylene glycol were assumed to be that being the major component of the de-icing solution. So in conclusion, we've gone through the entire design process that our team went through this semester. Some important points were that the final product achieves most of the customer needs. We assume it seems like it performs similarly to other ice scrapers, but we were not able to test the performance measures. We did do a cost analysis that led to a price that is very close to the desired market value. Perhaps more calculations and further analysis and redesign of subsystems would enable us to lower the market value even more. And an additional fluids analysis was performed in order to determine more information about the requirements of the pump, and if we wanted to be able to go forward and do more analysis and of the pumping mechanism in the ice scraper. But thank you for watching, and if you have any questions, feel free to post them in the comments.